Okay, good afternoon, everybody. Let's get started our afternoon session. And the first speaker is Tim Morris, who will be speaking about perturbatively normalizable quantum gravity. So half an hour, 30 minutes, please.
Thank you. Okay, so thank you very much for inviting me to talk at this very interesting conference. I want to talk about some work I've been doing with my students over the last 2 or 3 years, and it's on perturbatively renormalizable quantum gravity. So what I mean by that is not the usual way of treating perturbative quantum gravity as an effective theory, which is a valid thing to do, but you have to keep energies much less than the Planck scale. I mean a genuine continuum limit for the theory valid at all energies perturbatively, but computed perturbatively. Now, a genuine quantum field theory has a picture like this in the Wilsonian terms. And if it's a perturbative quantum field theory, the ultraviolet fixed point is the Gaussian fixed point. It just corresponds to the theory of free fields. And then in our space-time dimension, dimension 4, operators which have dimension greater than 4 are irrelevant. And that means that their couplings don't survive as separate couplings in the continuum theory. They just fall into the fixed point. The couplings that do survive are the relevant and marginally relevant ones, and they parameterize what's called the renormalized trajectory that shoots out of this fixed point. And they're operators of dimension less than or equal to 4. Now, as everyone knows, quantum gravity does not have a perturbative continuum limit. It's not perturbatively renormalizable. And in the Wilsonian way of looking at things, you can see this as follows. First of all, we need to write the theory in Euclidean signature so that the Einstein-Hilbert action looks like this, so that a Kadanoff blocking really makes sense. And then the natural coupling constant is 1 over the Planck mass or square root of Newton's constant equivalently. And to get a perturbative continuum limit, we expand around flat space. And then the Einstein-Hilbert action takes this form schematically. You've got the Fields-Pauli action of free gravitons. That's your Gaussian fixed point. And then you have an infinite series of interactions. And the problem is that all of those interactions correspond to irrelevant operators. Even the simplest one, the 3 graviton interaction, is dimension 5. And so none of these operators can have couplings that survive to the continuum limit in their own right. And the only, strictly speaking, the only continuum limit you have for gravity is that of free gravitons described by the Fields-Pauli action. Now, phrased in this way, quantum gravity has another problem, and that is that the action in Euclidean signature is unbounded from below. It has to be. It's proportional to the scalar curvature, and the scalar curvature can have arbitrarily positive or arbitrarily negative values. And if you follow the signs, it's actually the positive curvature manifolds that cause the problem. And that means this partition function, which is anyway a rather delicate concept, is not even naively well defined, because this exponential factor doesn't just provide exponential damping, but also exponential growth. Well, these guys way back in the 70s noticed this problem and showed that the problem lies in what you can think of as being, roughly speaking, the overall size of the metric, local overall size of the metric, the so-called conformal factor. And you can see this problem even at the free level if we take the fluctuation field and divide it into its traceless part, which you can think of as more or less the graviton, and the traceful part, which is nothing but this conformal factor. And then if you choose a gauge that decouples the two, you see that the conformal factor has the wrong sign kinetic term. So even at the free level, this action is unbounded from below. And we'll see that that could be key to solving the first problem, the problem of perturbative non-renormalizability. So there's one other thing I should have said. So these guys propose to solve the problem by integrating this conformal factor along imaginary directions instead. But what we will do is we'll take this minus sign seriously. It's forced on you by diffeomorphism invariance. And as I say, we'll see that it could be key to solving the first problem. Okay, so the idea then is that the partition function doesn't make much sense in this case, so we won't use that to define the theory. Instead, we'll use the Wilsonian renormalization group. Now, in the continuum, that's a functional differential equation, what Wilson called the exact renormalization group. And changing some signs in the differential equation doesn't invalidate that differential equation. So the idea is that we can't make much progress with that, which anyway was a delicate concept and needed regularization and taking a careful limit. And we'll use instead the Wilsonian renormalization group, which is the deep way of understanding how to take that careful limit anyway. Nevertheless, the solutions, this minus sign will have a profound effect on the solutions. And to emphasize that, I need to first review what Wilsonian renormalization group looks like with the right sign kinetic term. So let's take a scalar field, single component real scalar field with the right sign kinetic term. And for this, it's sufficient to take non-derivative interactions and linearize them. So epsilon is small here. Now, there are various versions of the exact renormalization group, but in these limits, they all collapse to the same thing, just this simple differential equation here. And what this tells you is how the effective potential changes as you lower this ultraviolet effective cutoff lambda. And as you lower it, you're gradually integrating out more and more momentum modes. And the idea is you start at some high cutoff, eventually infinite, and you integrate all the way down to 0, and that's how you do your partition function integral. Now, as you lower the effective cutoff at the linearized level, the only quantum corrections are tadpole corrections, and that's given by the right-hand side. The tadpole integral is this guy here. And since the tadpole integral is quadratically divergent, but regularized in some way by this UV cutoff, it goes like lambda squared. It's a one-loop integral, so it goes like h bar. And this a is just a pure number. It depends upon how you regularize. It's some non-universal number. Now, this then describes the Kadanoff blocking step of the Wilsonian renormalization group. The other step is to rescale back to the original size. And we can do that very conveniently by measuring everything on the scale of the effective cutoff. Do it simultaneously by measuring on this scale. In other words, we just change to variables which are dimensionless using this effective cutoff, these tilde variables. If you do that, and then you separate variables, then you get an eigenfunction equation. And this will give you the operators of definite scaling dimension, what I call the eigenoperators. Lambda here, little lambda is the renormalization group eigenvalue, and it gives you, in fact, directly the dimension of the conjugate coupling. So the conjugate coupling is this mu to the lambda here. Mu is just the usual arbitrary physical mass scale. Okay, well, the nice solutions of this eigenoperator equation are discretized, and they are just, in fact, the Hermite polynomials. And the scaling dimension of these Hermite polynomials is just given by the engineering dimension of the top term. And these other terms in the polynomial are just generated by these tadpole corrections. So if we followed this through, we would just reproduce the standard perturbative framework in this language. And in particular, you see that for n greater than 4, all of these operators are irrelevant. So their couplings do not survive the continuum limit in their own right. And you're left parameterizing the continuum limit by the couplings which are relevant and marginally relevant. So one other thing I forgot is to, it's on the next page. So what I call these operators the nice solutions. In what sense are they nice? Well, the point is this eigenoperator equation is of Sturm-Liouville type. So it comes with a Sturm-Liouville measure. And these operators span the space of perturbations which are square integrable under this measure. Now, this is a property of the exact renormalization group, which is little emphasized, but crucial to the Wilsonian renormalization group, because it tells you how to take an arbitrary perturbation and expand it as an infinite series over these operators of definite scaling dimension uniquely and in such a way that this series converges in the square integrable sense. And then from then on, of course, you get the full story because you see that in this case, infinitely many of these operators are irrelevant, so their couplings don't survive in their own right, and you're left parameterizing the continuum theory in terms of the relevant and marginally relevant couplings. Another thing to point out about this equation is that it's parabolic, and the Cauchy initial value problem is defined, therefore, in only one direction, and that's in the infrared direction. So what that means is that if you start with some UV potential, effective potential, you're guaranteed a solution if you flow towards the infrared, which is the direction you would hope the thing was well defined, since this is supposed to be describing integrating out modes from the UV down to the IR, where eventually you'll get the physics once you've done the complete integral. On the other hand, if you take this UV potential, effective potential, and try and flow in the UV direction, what will typically happen is that this potential will become singular. It'll develop cusps or distributional singularities, and after that, the flow ceases to exist. Now, you can understand that effect as physicists quite easily. This, under a small change of variables, this is nothing but the heat equation. And evolving it in this direction corresponds to the heat diffusing out as time increases. And you're always guaranteed to find a solution in that direction. But if you try and evolve it in this direction, you're trying to reverse the time flow, and the heat, instead of diffusing out and forming ever smoother configurations, will diffuse in and form these cusps or singularities of other types, after which the flow ceases to exist. Okay, now let's change the sign and make it a wrong sign kinetic term. So now we're describing at the linearized level the conformal sector of gravity, just purely the conformal mode. Well, you still have a flow equation. It's just that the sign changes on the right-hand side. So omega lambda now will stand for the magnitude of the tadpole integral, which is actually negative. And you can still change variables and separate variables to get an eigenoperator equation. It's just that you have a sign on the right-hand side. And this is still Sturm-Liouville type. So the nice solutions, the operators that we need to choose, are the ones that span the space of perturbations which are square integrable under the Sturm-Liouville measure. But here's the first surprise. The Sturm-Liouville measure is now exponentially growing. So for the interactions you have to choose need to decay sufficiently fast for this integral to be well defined. So you're forced to choose decaying interactions, and the operators that span this space actually also are exponentially decaying interactions. And they form this tower of operators. And the simplest one is dimension -1, and all of these are increasingly negative dimension. That's scaling dimension and actually also engineering dimension. And so remember, the operators are relevant if they have dimension less than 4. So you see that all of these are super relevant. I mean, they're all relevant. All of their couplings have a right to survive to the continuum limit. So we're in a very different situation. Now, the other thing is that with this change of sign, we still have a parabolic equation, but the Cauchy initial value problem is now well defined in the UV direction. If you pick some random initial potential and try and flow in the IR, you're guaranteed to find the flow will fail. You won't be able to integrate out all the modes, and the theory doesn't exist. So that's the reflection of the problem that you see rather more unfortunately in the partition function. But here it's not an obstruction, it's not complete obstruction, because we know this doesn't tell you that there are no initial actions for which a flow to the infrared exists. It just says you've got to be careful. For example, you can choose, in this simple case, you can choose the answer you want down here, and then the flow upwards, the diffusing out, is guaranteed to exist. And it will tell you that the bare potential that reproduces your choice down here has to be some rather smooth configuration at the UV. to guarantee that this flow goes all the way down to the infrared. Well, so you need to choose interactions which are square integrable under this measure. You can see this as a kind of extra quantization condition that's required, which will determine the parameterization you have to use when you're working with Einstein gravity. So if you start with some potential that is square integrable under this measure, then you can show that it will stay square integrable for all scales larger than the one where you started. And so this is kind of a UV condition, which is compatible with the renormalization group. Now, these operators are non-perturbative in H bar. That's because they're divided by this tadpole integral in the exponent. And this sort of e to the minus 1 over H bar behavior is typical of non-perturbative effects in quantum field theory. Instantons and renormalons, for example, go like that. But what that means is that we're going to have to treat the theory non-perturbatively in H bar. Now, that sounds like a challenge, and it is, but it's not insurmountable because we are allowed to treat the theory perturbatively in the couplings, because we're forming this continuum limit around the Gaussian fixed point. So perturbatively in the couplings, but non-perturbative in H bar, which means we'll have to sum in overall loops. Okay, so I emphasize that you have to choose your couplings carefully if the flow is to exist all the way to the infrared and thus the theory exists. Thus you'll be able to integrate out all the modes. Well, if you do that, then another effect takes over. You find that at some intermediate scale, lambda sigma, I've called it here, this potential will no longer be square integrable under the Sturm-Liouville measure. It exits this space. And at the point where it exits that space, its exponential decay freezes in. So you find that if you complete the integral and form the physical potential, you'll find that that physical potential decays with this characteristic scale, which is why I've called it the amplitude suppression scale. This scale is a function of all of these couplings. You can see it as a kind of collective effect of this infinite number of couplings. Well, let's put back all the modes, all the remaining modes for quantum gravity. The graviton has the right sign kinetic term, so it has an exponentially decaying Sturm-Liouville measure. And the ghosts can be chosen to have 1, 2. Both of these guys are give you polynomial interactions. So polynomials span the space of interactions in this well-defined sense, in the sense of being convergent and the square integrable sense. But dependence on the conformal factor cannot be polynomial. In fact, you must have dependence on the conformal factor because 1 is not square integrable under this. They have to be expanded over these delta operators. Now, for all the other fields, and in fact, for also differentiated fields, you can have arbitrarily complicated interactions. This is actually the Batalin-Vilkovisky antifields that will parameterize BRST invariants. You can have an arbitrarily complicated monomial here, but you can always find an n large enough, since these get increasingly negative, that the combined operator has dimension less than 4 and is so relevant. And so its coupling will survive to the continuum limit. So you see that the way that the theory organizes is that you end up with this monomial times a coefficient function, which has those couplings that survive. And there'll be an infinite tower because as soon as you find an n such that the combined operator is less than dimension 4, all higher n will also have a dimension less than 4. So there's an infinite number of couplings surviving in here, starting at some lowest value. Okay, well, that's the field content. How do we impose diffeomorphism invariance? And here you have to be a little bit careful because we have to work non-perturbatively in H bar. So we can't just say, oh, well, at the classical level, diffeomorphism invariance is this. So order by order in H bar, we know we have to deform it in this way. And that's how we get our BRST invariance and so forth. We've got to go straight to the answer somehow. You might think that's difficult, but it isn't really. We can rely In particular, on the most elegant way of sorting it out is to use the Batalin-Vilkovisky quantum master equation. So you can write that quantum master equation regularized by this cutoff. So these guys, I haven't shown it, but these guys are regularized in the UV by that cutoff in such a way that it's compatible with the flow equation. And then close to the UV fixed point where we just have free gravitons, you can expand the action. And then you find, relying on earlier work of Henault et al. Using the classical master equation, you find that these interactions are unique up to addition of BRST exact terms. And they just correspond to the usual classical ones that you would have expected to see. However, in this theory, we have an obstruction because these coefficient functions have to sit in front of every interaction, and they decay with this characteristic amplitude suppression scale, so they're non-trivial. And you can show that the fact that they transform is an obstruction to getting BRST invariants. So we would appear to have an impasse. However, notice that these guys decay with this characteristic scale. And thus, if we look at scales much less than this characteristic scale, these coefficient functions are basically constants. So this just says this. You can prove the solution exists only if f is independent of phi. But by sending this characteristic scale to infinity in physical scales, these things just trivialize and become basically constants, and you can recover the BRST invariance in a quite natural way. So let me give you an example. This is the 3-graviton interaction, which is already an irrelevant coupling. If you choose these underlying couplings in this way to be a power of the amplitude suppression scale times a proportionality factor, which happens to be mass dimension -1, then you can see that these couplings, the lowest coupling is actually marginal and all these higher couplings are relevant. And if you combine that with those delta operators, you get a coefficient function, which is a solution of the linearized equations of motion. So this is for first order interactions. And the physical coefficient function, which you get by integrating out all the modes, taking lambda, the limit lambda tends to 0, is just in this case, this exponentially decaying factor that you must have. But times this coefficient, this proportionality constant, which is negative dimension. Now, if we take the limit in which the amplitude suppression scale tends to infinity, this becomes just kappa. And at this point, we recognize that what we built here is Newton's constant, the square root of Newton's constant. But Newton's constant doesn't exist at the fundamental level. It's these relevant couplings that exist. Newton's constant is irrelevant, so it can't exist in the continuum limit at the fundamental level. But it is instead a sort of collective effect of all of these other couplings. An effective diffeomorphism invariant coupling that arises as a collective effect. Well, it turns out you can do this at second order. Life gets difficult, but you can push this to second order. You're going to have now 2 vertices in every Feynman diagram. That's your second order in coupling, but you have to work to infinite order in H bar, so you need to sum over these so-called melonic Feynman diagrams. The flow equation gives you, in fact, a closed form for that, and you can actually solve it in closed form. And you can then carefully treat that solution and check whether it's singular or non-singular as you go towards the infrared. Ensure that it stays non-singular so that the theory exists. And you can also ensure that the coefficient functions that are generated in that process all have the same amplitude suppression scale. And then you find that if you're careful, as you go to scales much less than this amplitude suppression scale, the modified Slavnov-Taylor identities are satisfied. And actually what pops out are just the standard perturbative quantum gravity amplitudes at second order, where also you recover Newton's constant. So this construction is crucially different from other quantum field theories and other conceptions of quantum gravity, but sort of falls out rather naturally from this insistence that we expand over operators that are span these square integrable spaces. So what you have is something that looks superficially like the standard story. You've got the Gaussian fixed point and the renormalized trajectory, but this part of the renormalized trajectory lies outside the diffeomorphism invariant subspace. You can't impose diffeomorphism invariance here. Diffeomorphism invariance, however, does arise naturally as you go to scales much less than this intermediate scale, this amplitude suppression scale. So at higher orders, it looks like you may need to introduce couplings. Effective couplings will survive just in the same way that they do in perturbative quantum gravity. So that order by order, you have to introduce new couplings. That's one possibility. However, we see hints that these couplings at higher order are determined by a non-perturbative effect. You see, so far what we've been handling is something that's non-polynomial in the conformal factor, but polynomial in the graviton. We know that's not true. Ultimately, diffeomorphism invariance forces you to have a theory which is non-polynomial in the graviton. Then you have to face up to the fact that the theory has a Cauchy initial value problem that's only well-defined in the infrared for the graviton and only well-defined in the UV for the conformal factor. Or to put it another way, in general, the flow is potentially singular in both directions. In this direction because of the graviton and in this direction because of the conformal factor. So you can investigate this schematically by just taking the linear equation again and junking all the bits that would allow you to enforce diffeomorphism invariance. So just taking this very simple equation, this is kind of in the spirit of how partial differential equations are analyzed in the maths literature. And you notice that then this equation is actually unclassifiable according to partial differential equations. Because it's parabolic in these two directions, at this level, you could decouple these two, but of course, once you introduce interactions, phi and h talk to each other. And so you have to proceed very carefully. In fact, if you cross out the left-hand side, what you have on the right-hand side is hyperbolic, and there are a continuous infinity of wave-like solutions to just that bit. So these are subtle equations to find solutions for. And what you can do at this simple level, of course, you can find solutions just by Fourier transforming. And if you take the Einstein-Hilbert action and expand it over vertices and insist that you parameterize the metric such that those coefficient functions all have well-defined flows, then you'll find that the higher derivative terms, like curvature squared and so on, are forced to have solutions that are not well-defined. So it would appear that perturbations, since we're considering linearization here, perturbations are not freely chosen for the higher derivative terms. So these couplings that would appear to be freely chosen aren't. Okay, so that brings me to my conclusion. What I've shown you is a construction that establishes, in this novel sense, quantum gravity as a genuine continuum quantum field theory at order kappa squared with all the correct properties. It just reproduces the standard perturbative quantum gravity. It appears to work at each order in kappa and would just require new coupling constants order by order, just as you see in perturbative quantum gravity. However, we see hints that these couplings are fixed at the non-perturbative level in order to get acceptable renormalization group flows. And I can stop there. Precisely half an hour, I think.
Yes, thank you. Exactly half an hour. So questions, Andy, please.
Well, thank you very much for this very interesting talk and this very, I would say, exotic approach to non-perturbative quantum gravity. So I have a couple of questions regarding this tower of non-polynomial interactions that you introduce. From the viewpoint of diffeomorphism invariance, is it actually possible to reformulate them covariantly as some functions of curvature instead of this separate dependence on the conformal mode actually defined on the flat space background and the transverse traceless graviton mode? So this is the question number one. And maybe if you would first, maybe later ask the second one.
Yeah, sure. So yeah, no, that's a good question. And of course, I've desperately tried to do that and have failed. You can go a tiny bit of the way. So you can, if you can think about expressing them instead in terms of the linearized curvature. And then you can write down operators that are a function of the linearized curvature. And that is a nice step in a way, because they then you can see that they have very similar properties, but the properties are independent of your choice of gauge. At the moment, these things depend upon the choice of gauge, although in a rather inessential way. But I haven't been able to see a way of taking them to a point where they're functions of, you know, the full nonlinear curvature in a way that seems to make sense. But maybe I just missed something.
Okay, maybe then as a continuation of this question is the following, that maybe in your formalism it is in principle impossible to construct them as covariant functionals of fully nonlinear curvature and metric, in the following sense. As I understand, in your picture of a Wilsonian approach, you actually, by introducing this, how do you call this, filter term in the vectoric equation or whatever, you always at finite value of the cutoff lambda, you always break diffeomorphism invariance of the formalism. And even though you can write down the correspondingly modified BFV machinery, still the formalism is intrinsically diffeomorphism, not invariant anymore.
Okay, yeah. So no, I think that's a misconception. It is what you seem to have at first sight, but it turns out to be, I think, a bit more subtle than that. So I didn't have time to go into this in great detail, but hidden inside these guys are regularizations of this quantum master equation, which preserve all of the properties of the quantum master equation that you need. I mean, 99.9% of the properties of the quantum master equation, which are useful, just come from the statistics. The fact that you have these opposite statistics antifields, and that's preserved. So all those beautiful properties that you have are still in here. Now, the crucial point is that this thing also is compatible with the flow equation. So what that means is that this thing is, if it's satisfied at one cutoff, you're guaranteed that it's satisfied at all. And in particular, in the limit that lambda tends to 0. Now, the interesting thing is, I mean, there are various ways of expressing this, but in this way of looking at it, in the limit in which lambda tends to 0, this Batalin-Dylkovitsky measure term disappears, and this just becomes, in fact, the Zinger-Stan equations, which give you the correct Slavnov-Taylor, unmodified Slavnov-Taylor identities, and you're guaranteed that your vertices satisfy that. I mean, I use that. That's why when you actually do this calculation, which is done in all gory detail at second order, you get the amplitudes that are equivalent to perturbative quantum gravity. So, where these amplitudes are transverse as they should be, and so on. what's going on here is a little bit more subtle than that, because imposing those modified identities puts you inside this space. And as I say, once you're inside this space, you're guaranteed to satisfy the correct identities when you finish integrating. But what I have are vertices which cannot satisfy even these modified vertices, except in the limit when they go down here. So to come back to I think your question's a beautiful one, and I'm thinking along the same lines now, which is, okay, these type of expansions, you're trying to fit a round peg in a square hole, and this is as far as you can go. And but nevertheless, the idea that the Wilsonian renormalization group has these peculiar properties opens a new window into thinking about how you ought to quantize gravity in such a way that you can reproduce this picture. What I've got here, I don't find very happy. I'm not very happy with it, but this basic idea that these flow equations have these peculiar properties could indeed be important for quantizing gravity properly, and you can do it in a way that's completely compatible with the BRST invariants, but you just have to take this slightly more subtle viewpoint.
Well, let me reformulate my puzzle, maybe in some other terms.
Okay.
You see, whatever you do with BFV formalism and master equation, whatever else, still you have behind the whole construction, you have the vectoric equation for the functional, which depends not on just one field, but it depends on two fields, two metrics. One metric, this is just a quantum metric of the mean value of the metric, and another is the metric which is introduced in this linear, or better to say quadratic filter term in the path integral, which makes all this Wilsonian stuff, right? So you have a 2-point quantity, and whatever kind of Ward-Slavnov identities you would write, you would still have this object which will not be invariant under the diffeomorphism of one argument. It can at most be done invariant with respect to simultaneous transformation of these two arguments. And then the question arises, how to construct really this dependence on the second argument. It disappears only in the limit when you put lambda to 0, right? This is just the...
Yeah. But that lambda tends to 0. You have to... So, I mean, sometimes people are a bit naughty and they try and extract physics from these ideas at non-zero lambda. And I completely disagree with that. Well, not completely. I mean, you have to try everything. But that is extremely dodgy. The strict point of view is that you can only get physics out of this once you've sent lambda to 0. So this is a way of taking that limit. There was never anything wrong with using a cutoff that naively breaks the symmetry. I mean, let's go back decades and decades when people used to use Pauli villas. There's never anything wrong with a cutoff that breaks the symmetry, but you just have to be very careful about how you take the limit, even more careful than you have to be if you use a cutoff that preserves the symmetry. But that's all done here. So you must do the integral and send the lambda to 0, and only at that point do these two fields that you're talking about, the background field and the quantum field, recombine into one object. So that you have to live with that.
Do you want to say that for lambda, for non-vanishing values of lambda, all your answers are gauge dependent?
Yeah.
The limit when lambda goes to 0, then you can construct gauge independent S matrix and all this.
And it's slightly better. That's exactly right. And it's slightly better than that, because if you insist on this at some non-zero lambda, you are then guaranteed, as lambda tends to 0, that you do get those gauge independent amplitudes.
But only in,
but only in the limit when lambda tends to 0. Yeah.
okay, thank you. Thank you. I think I have exhausted my, well,
No, thanks very much for the questions.
askable questions.
Okay. Frank Saurisik, you had a question, yes?
Yes, brief one about the three parameters that you have if you send lambda to 0.
Yes.
Is it really that there's only one, the kappa?
Well, at second order for pure quantum gravity, you don't actually, well, here's an interesting point. You don't actually have to introduce a cosmological constant. You can, but you are not forced to. The cosmological constant, the only couplings that you're forced to introduce are the ones you see perturbatively, which are forced by these logarithmic divergences. Mm-hmm. And you don't get logarithmic divergences in the cosmological constant. At least not this order. I don't think it's any order.
Nice.
Okay.
Okay, and the last question from Kumar.
My question is about your last slide.
Okay.
When you said the coupling constant must be fixed at non-perturbative level, and and you said you used the word acceptable RG flows. What is the definition of acceptable RG flows?
Yeah. Well, so the point, it's in this picture. So you need an RG flow that exists all the way from lambda equals 0 to infinity. And these equations have always the danger that that RG flow will just cease to exist at some point because things go singular. So that's an acceptable RG flow. I mean, if I can construct one that goes all the way from 0 to infinity, I'm basically done, right? Because lambda equals infinity corresponds to removing the cutoff.
Mm-hmm. And the question, suppose if you have more than one UV fixed points, is it acceptable? Is it okay?
Yeah, I mean, so, yeah, I mean, who are we to say? We may humanly find that unacceptable.
Most of the time, most of the times in the approach, you assume that only one UV fixed point, but this is not
actually,
necessary.
In my
when
work,
you have a non-perturbative approach.
Yeah. So in my work on quantum gravity, I mean, using simple models where you clutch something here or there, not this stuff that I'm talking about here. I often do find actually even continuous sets of fixed points, and is that and I don't know. That's either a problem of the approximation, or it might be saying something about the truth in a different framework, actually asymptotic safety. So, I mean, you have to keep an open mind about this. In this particular case, you know, I went very quickly over this, but in this particular case, you have some kind of analog. I've got the one fixed point, the Gaussian fixed point, but it looks like you have a danger of showing that you have a genuine continuum limit, but you just have an infinite number of couplings. And that's shocking, terribly unfortunate phenomenologically, but I don't actually see where there is, you know, a logical problem with that.
Okay. Thank you.
Okay, thank you again, Tim, and we can pass to the next talk.